Good morning. Today we are going to see on the application of overview of geosynthetics. See why geosynthetics. Just to recap memory. In the recent years, while providing a solution, engineer has to face several challenges. Various site constraints, space, alignment, time schedule, maximum usage of local resources, and then material, hence cost effective, least environment impact, and long term performance and higher cost benefit ratio. So the solution is use of proper geosynthetic material, because they offer the possibility to solve or drastically reduce the problems. There are certain deficiencies, there are certain functional requirements in various applications. Because these geosynthetic have got those functional properties, they will be able to do it. Just to give you an example, okay, this is, suppose this is a concrete and steel structure. You can make a structure like this, which is, stands against the gravity, a soil at an obtuse angle. It will be able to. It is just a demonstration. Somebody did it to bring out the demonstration effect of it. It is not actually useful. He did the whole thing. He made the reinforcement like this, then they removed it, and it stood for a couple of hours. So he said, that way the geosynthetic with the reinforcement effect and soil can behave like this. So yesterday Professor Rao has explained the function: separation, filtration, reinforcement, drainage, containment. When we go through various applications, you may find the requirements are either singularly or all these functions are required depending on the site conditions. So this is an example of a filtration, this is separation, this is containment, and this is bearing capacity improvement. So separation come reinforcement. And there are various products, just to give you, from Gabion, Polymer Gabion, Steel Gabion, rope, boulder net, that also we consider part of the geosynthetic. Barriers, prefabricated vertical drain, erosion control mat, as we call the RECPs, anchor drains, which are drain come anchors. And then GEOGRIDS, non-woven HTP membrane, geosynthetic clay liner. Geosynthetic clay liner is a GCL liner, which is 2 layers of textile sandwiching a bentonite, and all of them are needle punched together. And finally geocomposite. So when you have a functional property, when you require more than, for laying and other advantages, we can combine them. GeoGrid, GeoTextile and geomembrane. Any 2 of the 3 can be combined together to give a composite. That we will also see. So just to give you an idea, there is a grid, there is a non-woven, there is a woven, geonet with a textile, geosynthetic clay liners and geomembrane. And steel gabion, polymer gabion, prefabricated vertical drain, RECPs, boulder net, anchor drain. Now let us go to application. There is certain difference between the use and application. Use is, we have to use it for a definite purpose. When it comes to application, we also have to expect certain amount of performance out of it. When we apply it, there has to be a result, that is in terms of performance. So when you are looking at this, it can be classified in so many ways. Now what we are trying to classify it in infrastructure and environmental protection. Under environmental protection, you can take landfill engineering, coastal protection, rockfall protection, canal lining, flood control, which are all part of the environmental protection activities. Roads, railways, ground improvement are all part of infrastructure. This is just for our clear understanding. We try to classify it into two different things. So, road applications, you say reinforced soil wall, hard standage, slopes, then Gabion fascia walls, then a landfill in different types, coastal protection with Gabion, with geotube, with Gabion with different kind of structures, canal lining, then rockfall protection adjoining a railway line, erosion control, and track bed stabilization. That is, railway tracks are also semi-rigid pavements. They are also stabilized using the GeoGrid. But in all these things, it is not simple, straightforward. In the sense, you got a product, you just lay it. It is not. There are certain special requirements when you use them. In some cases, we have to devise a methodology or take the advantage of certain machineries, other thing has to be fabricated so that it is installed the exact way so that it gives us the desired performance. So in every one of them, that's also we will see as we proceed further in each application. And I talked about products, functions and composites. Then there is a basic material. If you take a textile, it's a basic material, woven textile or a non-woven textile. Now, they are converted for use as value-added products. Take a textile, you can make a bag out of it. Somewhere you make a tube out of it. So like that, a value-added product. So you can make a sand mattress out of it. So these are all value-added product which is developed further. So ready to use in the site to satisfy various requirements. Composite is one thing, value-added product is also another issue. Reinforced walls. So you can have reinforced wall like that because normally it is not possible to make the soil stand vertically. So with a cladding, just with the facing element, with the reinforcement, we can make the soil stand, which is reinforced soil wall. And you can get beautiful curvature out of it. And you can have different fascias type. This is what yesterday he said. This is a full-height panel, where the grids are already embedded and a tail is attached to this using a bodkin kind of a joint. So that there are advantages in this method. It should be used in very specific cases. Your requirement of a crane to lift, see, even a panel normally weighs around 1 ton. Suppose you are making a single panel of this type, which is about 5 to 6 meter height, it will be very heavy. But you require, the requirement of the crane for putting it in position is only 1 time. Because basically initially you hire the crane and you put it all in position. Then give a support from external support. Then all you have to do is attach the grid as you come up with various layers, put the fill material and compact it. So that way the execution can be much faster. This is both sides, and this is what he said. This is a wall which can be which was constructed over an existing wall, and you have got various fascias: full-height panel, incremental panel, segmental blocks, Gabion fascia, and steep slopes. A wall is something which is around 90 degree, but with a pattern of 4 to 7 degrees. Whereas a slope is anything up to 70 degree is called slope. Above 70 it is called wall, below 70 it is called slopes. So, why reinforced soil wall? It's an application. So, we have to understand, occupies very little space, less site preparation and minimum excavation, because the embedment depth is only, most of the cases, only 1 meter. So, less site preparation, simple and rapid construction, flexible to withstand differential settlements, and it can also better seismic. Yesterday he showed, I think he showed here, in the Japan, the earthquake and other thing, where the conventional structures, he didn't show it, probably he will show it. The conventional structures failed. But in the case of these kinds of walls, reinforced soil walls, they are flexible in nature. Flexible is a relative comparative term. Compared to a rigid structure, they are flexible. And when a flexible structure is there, what happens? When it is subjected to even seismic forces, it yields, but it is not failing. There is some movement, but the structure is still safe. So that is the advantage of this. And if you look at it in most of the application, it is about energy dissipation only. I always used to say, example, if I bang my hand against this hard surface, it gets hurt. Why? The forces become reflective. If I bang it against a curtain, the curtain moves depending on the force. But once the force is removed, it comes back to original position. So there is a movement, associated movement dissipates the energy. This is the basic principles of. Based on this only reinforced soil walls are constructed, slopes are constructed. Again in pavement, there is rigid pavement, flexible pavement, semi-rigid pavement, hard stand edges. All these geosynthetic use in all these applications. Semi-rigid pavement is a railway track, and flexible pavement is a BT pavement. Rigid pavement is a concrete pavement. And hard stand edges and stockyards, which are normally built near the port area, where a lot of containers, trucking and materials are stocked. There the load is, static load is very high. This is also associated with dynamic loading, but the dynamic loading movement is very slow. The crane or the trucks move very slowly. So we have to cater to very heavy load and other things. For that also used. That's also a type of payment. So payment is a structure. Generally we say it carries a vehicular traffic. And what are the various components? There is a subgrade, the natural earth which is available, or the alignment, along the alignment where you are going to construct the road of whatever type. Then you have got a granular layer. The granular layer consists of two components. One is subbase, other is base. The base was originally called WBM, now it is called WMM. WBM means water-bound macadam, WMM means wet mix macadam. Okay? Just the terminology has changed and the method of placement has changed. And these are the foundation of the pavement. These two are there, the foundations. The real structural thing comes about in paved roads. There are unpaved roads, rural roads and hauled roads are all unpaved in nature, because that is sufficient for the purpose. When you want vehicular comfort, the movement has to be done very smoothly, then you have the paving, and that is bituminous layer. So the vehicle moves over it. So in this case, in the pavement, I am just going to give you an idea. I mean, each one is a separate topic. You can go into detail much later, I mean in other lectures. But what is the best position? If you want to, you have got a situation where you have got poor CBR value and then very high water table. A combination of both are there. So you can't even walk over that. The moment you put a geosynthetic, it will work both as a restrainment cum reinforcement layer. The subbase and base material which you paste over that gets interlocked, or purely in the case of woven textile, it's purely friction. By this action, the total rigidity of it is one. When we talk about a reinforced soil wall, we say the grid along with the wall fill is the total wall. It is not just, it is a reinforcement, there is a wall fill, but there is totally a wall. That's what we say, correct? Similarly here, the geosynthetic with the material placed about it acts in unison. So the total rigidity improves. The moment the rigidity improves, what happens? The dispersion of load is able to take on a much greater angle. That means it will be, the load will be coming over a larger area. That means the stress level coming, the same load without reinforcement and with geosynthetics, there's a difference. It is over a larger area, stress level is less. So in pseudo it looks as if the bearing capacity is improved. But we are not doing anything to the soil. We are not improving the bearing capacity. But the load transfer mechanism gives the feeling as if the bearing capacity is improved. Generally by thumb rule we can say the bearing capacity is X. By using the appropriate geosynthetic you can improve it to 2.5 to 3 times. And depending on, of course the influence is always, it's got a boundary effect. You place a reinforcement, the interlocking is effective up to certain depth only. So if you have, by design, the load, the CBR value, other thing, you require a very large conventionally base and subbase, and the thickness is more, probably you may have to use multiple layers of reinforcement. Okay? But that is an unpaved road without reinforcement. This is what happened. Poor bearing capacity, this is what will happen. But if you have the same thing, you have used a geosynthetic, then probably it will be able to. There will be small rutting, this unpaved road, but still the traffic is able to move freely without getting bogged down. And because I said there is going to be a, there is going to be a rigidity improvement. So if I want the same amount of thing, I use the thickness of X without geosynthetic. If I use a geosynthetic, I can reduce the depth of subbase and base layer. So there is a reduction in that for the same amount of load transfer, correct? That means a saving is affected, and today the circumstances, the natural materials are hardly available. Professor Rao is saying that is by 2030, because of the Paris Agreement, which India is a party to that, we are not supposed to use the sand, soil, other materials, and we have to use some other material. Already we have started using fly ash, then they say we have to use waste material also. If that is going to be the case, this is the real thing which is going to come and help you. So there is a reduction. So if you look at it in terms of cost aspect, here you have got so much of thickness, it has got certain cost. But here you have got reduced thickness, but you have got extra is the geosynthetic material, which has got a cost to it. What is the total cost of this versus this? And the difference in performance, reduction in maintenance, the long life, all other things, if you do your life cycle cost, gives you the benefit cost ratio, which will always, you will find in individual cases, you work it out, you will find always it is more than 1. In some certain cases it goes as high as 3. So just an example. This is what we can do for every project. You have to do the life cycle cost. Take into all the other tangible benefit, direct benefit, indirect benefit, everything you can put it, add a value to everything, then you can arrive at a benefit cost ratio. So this is what happens, and this is what is happening when you put a grid. There is a interlocking. So summary of the benefits: reduction of aggregate material up to 30 to 50% depending on the strength, CVR, the axle load, and what you are designing for, how many million axle passes, all these things there. So it's in the range 30 to 50%. Increased design life. Increased design life, I can explain to you very simply. Because the aggregates get interlocked with the geosynthetic material. Otherwise, you know, when a moving load is there is a bending and releasing action in a flexible pavement which is not visible to our naked eye. But when they are interlocked, this mechanical, due to bending and motion, otherwise the aggregates move apart, as is shown, that is prevented. That means it can get itself interlocked for a much more million axle cycles than originally. That means the road is not going to fail for more axle loads. So that is why increased design life, increase in bearing capacity I already explained to you, reduction in differential settlement, because it's a flexible draft, there is a reduction in differential settlement. Please note, in geosynthetic we never say we try to control the settlement. Settlement cannot be controlled except in the case of ground improvement where we adopt a different methodology, that we will see later. The access over very soft soil, some sites you cannot even move over to the site with your construction equipment. It's all made possible. Spanning over voids, because the geosynthetic can arch. It can have an arching action. Even if there is a void, the load transfer takes place over the gap to the next point. So it is an arching action. That is what we call it, spanning over the voids. And then finally, prevention of aggregate penetration and mud pumping, which is generally fouls the soil and results in so many other failures, which we see: rutting, fatigue cracking, reflection cracking, etc. But as I said, the pavement consists of two parts. One is the foundation, other is the BT. The unpaved road portion and with the BT. Now, suppose we take, for a new road it is okay. I can plate a geosynthetic material at the subgrade subbase interface. But if the road is already constructed, it has exceeded design life or it has poorly constructed, whatever reason it has failed, what can I do? That is existing road. That is where the asphaltic reinforcement comes into effect. That is a material, a grid or a textile or a grid and textile which can withstand the inlet temperature of more than 160 degrees, can be used, which has got very high strength and very stiff grids. These materials are used in the asphaltic layer as asphaltic reinforcement. Normally a crack appears, we go and redo the surfacing, after some time the crack reappears. This is arrested, this is called asphaltic reinforcement. Now, this is just to show you some pictures. This is how the grid is laid over the prepared surface. Now you see in the laying there is an overlap. That's how it is laid. It's ready for receiving the other granular material above it. Similarly, a textile can be used also, which works by friction. And this is the example for asphaltic reinforcement. There are certain procedures. The existing road is milled, graded, then you put a tack coat, lay the grid and material over it, then move directly over it. And the paving which you do, originally they started in the research with 100 mm. Now in most of the cases what you require is only 25 mm pavement. That means so much reduction in the BT material, which is which is very costly. And in performance wise, this has been compared with the modified bitumen and other methodologies, and it is found to be very effective. Then ground improvement. What is ground improvement? I said that the soil is not, or the place where we are going to start the construction, it is not suitable for the construction activities because of its poor quality and the type of structure that we are trying to build over this. So the ground has to be improved. And mostly it is in clay soil and soft marine clay kind of a soil. So normally what we have to do in that case, conventionally we have to do is consolidate the soil. The consolidation is a very long-term process. It takes years for the primary consolidation itself and then secondary consolidation. But what is involved in the consolidation process? The moment you have to do the consolidation test, the moment you put a load, first the load is taken by the water which is in the spaces, and slowly the water, if you have a drainage arrangement, the water slowly drains out. In the process the load is transferred to the particles, the clay particles, and they come together, they get compressed, and this is the whole process. Now what we have to do? We have to put a load, we have to provide a drainage path. If we do both that, probably we will be able to accelerate the entire consolidation process. And this is what is done by using a PVD. This is a channel, a core material which has channel. Over this there is a filter jacket, and this is installed using a crane, vibratory crane with a mandrel at the bottom which has got a plate. In 3 seconds you can install up to 20-25 meters. So there is a design methodology, how many things, what is the pattern, other things are there. That's all different issue. But for us, once it is done, then the whole thing is provided with a layer of high strength woven textile with some permeability or a non-woven textile, and then preloaded. And the preloading is also done in stages. You can't just put the entire loading at one go, because the moment you put the load, the pore pressure is going to build up, and you have to give time to pore pressure to dissipate. So it is a sequential construction, but still what is expected to take for the normal consolidation process years, you can complete it depending on the surcharge and the PVDs which you have designed in maybe in 6 months time. And there is a calculation which shows what is the anticipated settlement and what is the final settlement, which are calculated by using various instrumentation, piezometers and other things, and then we come to the conclusion reasonably the secondary settlement, everything has taken place, the ground improvement is complete, then we proceed with our structures. So this is an example of a very large area, Vizag Airport, where the runway, taxiway, apron, everything was stabilized using a PVDs and a high strength woven textiles over it. Okay, in those days about 500,000 square meters of materials have been used. And this is a view.